Thermal energy. Thermal energy is related to the kinetic energy of the particles in a sample of matter. Actually, thermal energy is the total of all the kinetic energy of the particles in a sample of matter, plus all of the potential energy of those particles as well. Some materials are very good at conducting thermal energy, which means that thermal energy can move through them very easily. Some are not so good. We can measure how good those materials are at transferring thermal energy with thermal conductivity. So this is the rate at which thermal energy is transferred through any given material. It's a numerical constant that's unique for each material, and metals typically have high thermal conductivities. So nonmetals tend to have low ones. So how do we know that metals are good thermal conductors? Well, metal objects tend to feel pretty cold compared to non-metals. So if you're outside in the winter and you are holding onto the metal handle of a shovel, it might feel really cold to the touch because the metal is really good at conducting the thermal energy away from your skin. It has a high thermal conductivity. If you touch the wooden part of the shovel handle, it will feel warmer to you, even though it's at the same temperature as the metal, because wood's a much better thermal insulator. It does not transfer the thermal energy away from your skin as quickly as the metal does. Thermal conductivity is measured relative to air, so the value for air is 1.0 by definition. Silver, by contrast, is 17,000, so that's a much higher thermal conductivity. Heat is a term that we often use interchangeably with thermal energy, but really we shouldn't. Heat is actually a transfer of thermal energy between objects or materials. We can determine heat energy transferred using this formula. So E sub h is the heat energy transferred to or from a material in joules. The m in the formula is the mass of the material in kilograms. C is called the specific heat capacity of the material, measured in joules per kilogram degrees Celsius. This is also unique for each material. Specific heat capacity is the amount of energy required to increase or decrease the temperature of 1 kilogram of a material by 1 degree Celsius. And here are some typical values. If you look at this table, you can see that water has a very high specific heat capacity. It's not the highest one in the table. We can see that hydrogen is the highest value in the table. You'll notice that in the table, the units here show us that specific heat capacity is measured in joules per kilogram per Kelvin. But a change in temperature of 1 Kelvin is equivalent to a change in temperature of 1 degree Celsius. So these values are the same if they're measured in joules per kilogram degrees Celsius. So here's water, a pretty high value, which tells us that in order to change the temperature of water, it requires a large amount of energy. So boiling a pot of water actually requires a great deal of energy. Whereas if you wanted to increase the temperature of some copper, that would require much less energy, more than 10 times less energy, because copper has such a low specific heat capacity. So in this formula, delta T is the change in temperature in degrees Celsius. So how much energy is required to increase 4.5 kilograms of water at a temperature of 5 degrees Celsius to its boiling point? Well, let's try the new formula. So here we've got mass, 4.5 kilograms, times specific heat capacity of water. I'm using 4,180. I used a different table for that, but that's okay. And then the change in temperature will be temperature 2 minus temperature 1, so 100 degrees Celsius minus 5 degrees Celsius. And when we work that out, we get 1.8 times 10 to the 6 joules, or 1.8 megajoules of heat. Sometimes we mix materials and they will both change in temperature. We call this heat exchange. When two materials at different temperatures are mixed, the heat is always transferred from the hot material to the cold one. It can never be reversed. After a short time, the mixture will reach an equilibrium temperature. And we can use this formula to show what happens. So C stands for cold, and H stands for hot. You'll notice here that on the hot side of the formula, we have a minus sign. That shows us that the hot material is losing energy, whereas over here, this is assumed to be positive because the cold material is gaining energy. So again, the C means cold and the H means hot. And I covered the answer to that question already. Let's try an example. A 500-gram piece of iron at 340 degrees Celsius is placed in a 1.5 kilogram sample of water at 10 degrees Celsius. Determine the final temperature of the mixture. So we'll try our heat exchange formula. We'll substitute in the values that we have. The mass, remember the mass has to be in kilograms. So 500 grams is 0.5 kilograms. So we had to change this one. We had to convert that one from grams. We have the specific heat capacity of water over here, and we have the specific heat capacity of iron over here, 460 joules per kilogram degrees Celsius. So we'll do some multiplication here. And the rest is just algebra. We'll get our T2 terms together, we'll collect those like terms, and then we'll divide both sides by 6,500. And we get 21.7 degrees Celsius. So you can see that even though the iron starts at a really high temperature, 340 degrees Celsius, it doesn't affect the temperature of the water that much because the water has such a high heat capacity, and the mass of the water is 3 times as great as the mass of the iron. So not that big a change in temperature for the water. But it's a huge temperature change for the iron. And that's an introduction to thermal energy and heat.